Today I'll be talking about conformal field theories and the conformal bootstrap. And what I want to try to describe is, first of all, what conformal field theory is and what it's good for. And then some recent developments that have happened over the past decade that have started sort of a revolution in our understanding of conformal field theories and our ability to do calculations. Okay. So conformal field theory, as Flip mentioned, touches on many different areas of theoretical physics. But maybe the most familiar area is the notion of critical universality in condensed matter systems. So let me start with that. So probably the most well-known example of a critical point occurs in a ferromagnet. So if we have a magnet and we consider the response of the magnet to applying a magnetic field, so let's turn on a magnetic field H and measure the magnetization M, then the magnet behaves very differently in different temperature regimes. So at very high temperatures, thermal fluctuations tend to sort of average out the spins in the magnet, and you get this smooth reaction to a change in the magnetic field. At very low temperatures, the spins want to align with each other, and there's nothing preventing them from doing that. So if you turn on a magnetic field in one direction, in the positive direction, you get a positive magnetization. If you turn on a field in the negative direction, you get a negative magnetization, and there's this discontinuous jump between the two behaviors. So these behaviors are obviously very different from each other, and there's an interesting transition that occurs at a very special temperature, the critical temperature. That's the crossover between these two behaviors. And at the critical temperature, the material, the magnet, displays some pretty striking behavior in various observables. So one example is the specific heat. You can measure the specific heat of the magnet. It depends on the temperature in this particular way. And there's some funny power law. The specific heat is proportional to the temperature minus the critical temperature to the minus alpha for some alpha that I'll show in a moment. And you can also measure the susceptibility, which is the response of the magnetization to the magnetic field. And this also has some funny power law with some funny quantity. Okay, so these exponents and power laws are characteristic of this kind of transition between these two behaviors. There's another example of a critical point that's pretty famous, which is the critical point of water. So we're most familiar with water in this region of the phase diagram. So the idea is that normally water is either a liquid or a gas, depending on the temperature. But if you go to high enough temperatures and pressures, there's actually a point where the distinction between the liquid and the gas disappears. And by the way, this phase diagram is not exactly correct for water because this line goes in the wrong direction. But you ignore that for the moment. This is supposed to be sort of paradigmatic for liquid vapor transitions. So we're just interested in this part of the plot. So there's this funny point where the distinction between the liquid and the gas disappears. And at this point, you can make measurements of various quantities in water. So one thing you can measure is the specific heat, which is the response of the material to a change in temperature. And so this is natural to measure in both the magnet and water. And it displays some funny power law in the case of water near the critical point. And another thing that you can measure is the compressibility. So sorry that this line hasn't made it on the slide, but you can guess what it says. The compressibility is something that has this same funny power law form. And the compressibility is something that you wouldn't want to measure in the magnet. I mean, you could, but it is not the most natural thing to measure. The compressibility is the response of the system to a change in pressure, change in volume. Okay, so there are these two things you can measure, and they have interesting power laws. And just as an example, here's a plot of the heat capacity in the temperature-pressure plane, and you can see that indeed these power laws are these very striking features in this plane. Okay, so now I'm going to tell you something that if you haven't heard it before should blow your mind, which is that these two systems, a magnet, which you can think of as a bunch of little spins that are in some magnetic field and they're flipping up and down, and a liquid, they have different observables. So in one case, it's interesting to vary the temperature in the magnetic field, and in another case, it's interesting to vary the temperature and the pressure. Those don't obviously have anything to do with each other. But actually, the numbers that appear in these funny power laws are the same. So these numbers are called critical exponents. And if you measure them in these two systems, so doing very different types of experiments, but if you measure these power laws, you find out that they come out the same. And actually, there are many, many other systems, not just ferromagnets and water, but other liquid vapor transitions. You could have magnets of many different types made of many different types of materials. And there are also quantum systems, which I won't have too much time to talk about here, but quantum as opposed to statistical systems that also have these funny power laws and also have the same numbers appearing. So these numbers are constants of nature. They're something that nature knows about. If you like, they're on the same status as pi and e. They're some numbers, and there's some interesting truth hidden in these numbers and their existence, and we'd like to know more about them. Now, so there's an even, to people taking physics classes and not playing around with magnets and boiling water, there's an even more famous example of a system that displays these numbers, which is the 3D Ising model. So this is something that you learn about probably in thermodynamics class. The 3D Ising model is a system of spins. So you have a lattice, and there's a spin on each lattice, a classical spin that can be either plus or minus 1. And the Hamiltonian is just sum of products of nearest neighbors with some overall coupling J. So this is a statistical system that you can study. You can write down its partition function and try to do computations with it. And it's supposed to be a model for a magnet. And indeed, it displays this same sort of behavior as a magnet. If you apply a magnetic field, then, which is, well, I haven't written the applied magnetic field in this case, but if you perturb this system, then it has two different behaviors at high and low temperatures, and there's a crossover point. And at the crossover point, you get these funny power laws, and the same numbers are popping out. And this is a particularly nice one to think about because it's very clean mathematically to state what it is. But it's also kind of amazing that out of this very clean mathematical system, you get the same numbers that appear in these real-world systems. OK, so why on earth is this happening? What are these numbers, these funny constants of nature, and how do we calculate them? So the fact that many different systems are described by the same numbers is called critical universality. And basically what we want to do is understand what leads to critical universality. OK, so that leads me to the next topic, which is conformal field theory, which is supposed to answer these questions. Before I go on, are there any questions about what I've talked about so far?
So for the 3D Ising model, can you calculate those numbers as you get for water and the magnets you measure it, right?
Right. So in the 3D Ising model, one thing you can do is simulate it on a computer using a Monte Carlo simulation. And that, until recently, was the best way that we had to calculate these numbers. It's sort of like making a measurement when you're doing a Monte Carlo simulation. Other questions? Yes?
You mentioned that the water and the magnets. How about the other materials? Do they all exhibit this universality?
Right, that's a great question. So first of all, there are many materials that all exhibit these same numbers. So we say that all of those materials are in one universality class. But there isn't a unique universality class. So there are other groups of materials that all display a different set of numbers, and that's a different universality class. So one of the things we'd like to do is, first of all, understand the numbers in the 3D Ising model universality class. But we'd also like to understand how many universality classes there are, and what are the numbers associated with each one. Other questions?
A simple one. Are they limited? You get into the answer. Is it a limited number? number, like 10, or is it like an infinite number?
So that's a fantastic question. It's an infinite number, but the space of universality classes is incredibly complicated, and it's basically one of the main things that well, high energy theorists, as they call themselves, have been exploring over the last 30 years. Basically, people have just been constructing, among many other things, they've been constructing more and more elaborate examples of universality classes that you can definitely show are distinct from each other. And there are many different constructions as of this point. Now, the question of how many actually can appear in laboratories is a different question.
I mean, the interesting question at that point is you look at the material and decide it's in this particular one. You actually have to measure it.
Right, right. So that's a great question. So it turns out that universality classes, even though there are many of them, are still very constraining. And you can imagine a situation where you have a material and you can make a very rough measurement on the material. And then if you have a classification of universality classes, you can know just from the rough measurement which universality class it lies in. And then you might know, then you know everything about the critical point of that material. So that's actually the goal, one of the goals, main goals of this program, to write down, to figure out what all the universality classes are, figure out everything about them, and then you have basically an encyclopedia that you can look at anytime you get a new material which has a critical point. And you just have to figure out which entry in the encyclopedia it corresponds to. That would be the dream. And that is a dream that has been realized in some special cases that I'll talk about later. OK, other questions?
Are there an infinite number of them? Infinite number of universality classes?
Yes, there definitely are.
Are one of them better than the others in some sense that we more?
So one thing you can ask is how many degrees of freedom there are in a given universality class. And that's actually a well-defined notion. And so the ones that are relevant for experiments are the ones with a small number of degrees of freedom. The Ising model conjecturally has the smallest number of degrees of freedom of any critical point in 2+1 dimensions, in 3 dimensions. Those will be the ones that show up in experiment because you have a limited number of things that you can put into your material. Many of the examples that people have been studying in high energy physics involve very large numbers of degrees of freedom in the limit that those numbers go to infinity. And so those are also interesting, but mostly theoretically at this point. Other questions? OK, so let me go on. So conformal field theory is a special type of quantum field theory that is capable of describing these transitions. And to understand why that is, let me go through the things that make conformal field theory one by one. So the first observation is that materials at these types of transitions, at these critical points, display an extra symmetry, namely scale invariance. So this is a picture where, on the left, what we've done is simulated the 2D Ising model and then taken a snapshot. Each square represents a spin, and the square is black if the spin is up and white if the spin is down. So this is an arrangement of spins that you get after simulating the 2D Ising model for a while at the critical temperature. On the right is a snapshot of the exact same, at the exact same time, where we've zoomed out from this simulation. And now each square represents a set, a 3x3 set of squares from the original set. And we color it according to majority vote. Okay, so a black square means that at least 5 out of the 9 spins is up. And a white square means at least 5 out of the 9 spins is down. And the thing to notice about these two pictures, so this is a zoom out of this, are that they look roughly the same. They have roughly the same types of black and white structures. If someone presented you these two pictures, you couldn't tell which one was the zoom out of the other if I hadn't told you. And I actually have a movie to illustrate this. So this is a simulation. Whoops, sorry about that. This is a simulation of the 2D Ising model where it starts out, we start out with a random state. So we randomly choose up or down spins, and then we're going to evolve them in a Monte Carlo simulation. And each of these is a different zoom level. And you can see that with the random state, the different zoom levels look very different from each other. So for example, which one is the most zoomed in? Right. The one on the right is the most zoomed in, and the one on the left is the most zoomed out. So what we're going to do is we're going to evolve this system. And what I want you to do is pay attention to compare each slide and see what happens to them relative to each other. OK, so the slide on the right is moving the most rapidly because it's the most zoomed in. And the slide on the left is moving the least rapidly. But aside from the speed at which they're moving, just sort of squint and look at them. And you can see that the state that the system settles into is very different from the random state. In particular, these first two slides look pretty similar to each other, again, in the same sense. They kind of have black and white structures of the same sort of size. And these are moving faster, so it's a little hard to see. But again, they show a lot more similarity to these states on the left. So this is the phenomenon of scale invariance. And this is a generic thing at these critical points that the system becomes invariant under rescaling, kind of like a fractal. So there's an amazing thing that happens in systems with scale invariance that satisfy a few additional properties, which is that very often scale invariance actually implies invariance under a larger set of symmetries. So you might start out with rotational symmetry and translation symmetry, and you know that the theory is scale invariant. But actually, you get extra symmetries for free. The idea is that if you have a theory that's rotationally invariant and scale invariant, then you can imagine, and it's also local in the sense that the dynamics at this point only kind of cares about what's happening nearby. Then you could imagine doing a transformation that locally just looks like a rotation and a rescaling. But maybe it's a different rotation and rescaling near different points. But because faraway points don't really talk to each other, that shouldn't really matter. And you can imagine that maybe this is a symmetry as well. And this is the definition of a conformal transformation. It's a transformation that locally near each point looks like a rescaling and a rotation. And this is my favorite picture of a conformal transformation. This is a drawing due to Escher of a boy standing in an art gallery who's looking at a painting. The painting contains a city. The city has a building. And the building is the art gallery that the boy is standing in. So globally, there's something amazing happening in this picture. But the reason it doesn't look like complete nonsense is because locally, near each point, the transformation that takes you from a regular picture to this one is not so bad. In particular, you can see, for example, with the window panes, that whatever these called, these upward struts and the vertical struts and the horizontal struts are at 90 degrees from each other. So if you zoom in really far and you don't care about the global structure, the picture looks kind of normal. And this is a conformal transformation. And on the right is the grid that Escher hand drew to help himself make this painting. He drew this without knowing anything about the mathematics of conformal transformations or holomorphic functions. And he also did it without Mathematica. OK, so conformal invariance is actually something that we get at these critical points. And conformal invariance, not just scale invariance, is extremely powerful. And we'll see why. So the last thing I need to explain in conformal field theory is the field theory part. So why is field theory relevant to these systems? One quick way to see this is to think about this 3D Ising model. So if we compute the partition function of the theory, we have a sum over configurations. So we're summing over all possible configurations of up or down spins of e to the minus beta h. And I've absorbed beta into the coupling j here. Okay, so this is the partition function. And you should think of this sum as a sum over a space of functions. So each configuration of spins is a function from the lattice to plus or minus 1. And so we have all these possible functions, and we're summing over them in this sum. So it's kind of like, if you squint, it's kind of like a path integral. So in the case of a path integral, we have a function s from a continuous space-time to continuous numbers. But you should think of this as kind of a model for this. And the study of path integrals is quantum field theory. And indeed, when you take the limit where the lattice spacing goes very, very, very small, so that you can approximate this lattice as continuous. And if you look at regions where you have many spins, so you can sort of average their contributions, and you can, instead of having plus or minus 1, you'd have some sort of average spin, which is a real number. Indeed, these two systems become related to each other. So the study of the partition function of the 3D Ising model is a study of path integrals, and that's why we can use quantum field theory for that. OK. Questions? Yes?
Kind of looking back to the Ising model video you showed.
Sure.
I hadn't thought about it before, but should you scale the time too?
Right. So the notion of time in that simulation is just a notion in your Monte Carlo simulation. So the way the Monte Carlo simulation works is you're basically trying to explore the space of states that are important for computing the partition function, the most important states. And the way you do that is by jumping through the space of states. And on a computer, you would ideally want to jump through that space of states as fast as you possibly can. And the time is the rate at which the computer is capable of doing that. So it doesn't really have, I don't think it has physical significance in the case of that simulation. There are situations in which time is important in conformal field theory, and I can talk about that afterwards if you like. It's a little bit confusing to just say in a few seconds here, so we can talk later. More questions?
Can you go back to that? So the previous slide?
Yes.
Is the right-hand side, is that a real grid representing this?
Yeah. So this is the grid that he drew.
So can you rotate that into a normal grid and see what the figure looks like?
Yes. So actually, there's a really beautiful there's a web page about this. So some mathematicians studied this transformation and wrote a really nice paper about it that I recommend you Google for. So Google Escher print gallery, and you'll find it. They identified the conformal mapping that he wrote here. It has to do with some interesting modular transformation of the torus. And then you can undo that mapping on the picture and unwrap Escher's drawing.
They actually have a figure of what
Yes. Yeah, they do. Yeah. Yeah. It's beautiful. I mean, you should look at it. It's different from what you would expect, but yeah, it's a sensible picture. OK, other questions? OK, so conformal field theory. So we've described why the word conformal is there, and roughly speaking, why the word field theory is there. So now let's talk about the elements of conformal field theory. Our overarching goal is to try to explore this structure as much as possible and push it as far as we can. And hopefully, by exploring everything about this structure, we can learn something about these numbers that I talked about at the beginning of the talk. So a conformal field theory has a few different things in it. So one thing that it has is local operators. So local operators are basically the different types of measurements that you can make that are associated with a point. So for example, in the case of a magnet, we could measure the magnetization at a point, or we could measure the energy density at a point. And in a liquid, we might measure the density of the liquid at a point or the energy density at a point. And actually, there are many, many other things that you might like to measure. For example, in a magnet, you could measure the product of magnetizations of things in a little spiral shape, where the spiral is near a point. So there are lots of things. There are an infinite number of things that you could measure at a point, and these things are called local operators. And so we give them names: sigma, epsilon, etc. Local operators have scaling dimensions. So if you measure a correlation function of local operators, so for example, we have a spin over here and a spin over here, and we measure the average of the product of those spins, then in a conformally invariant theory, that two-point correlation function is constrained to take a very special form. So it's a power law of the separation between the 2 points with some characteristic number here. And that number is called the scaling dimension. And these scaling dimensions are actually directly related to the critical exponents that I started the talk with. So our question about calculating critical exponents becomes a question about calculating scaling dimensions in conformal field theories. OK, so we talked about two-point correlation functions. You could also consider three-point correlation functions, where I measure the product of the energy here, the spin here, and the spiral here. That's a perfectly valid thing to compute. And those are proportional to some numbers. And one of the amazing things about a conformal field theory is these three-point correlation functions and these scaling dimensions actually determine every other correlation function you might measure. So this is a vast simplification over general quantum field theories. In a general quantum field theory, you really need to measure everything. You need to measure scattering amplitudes at 10 GeV and 100 GeV and 1000 GeV, and they are all different and they're not simply related to each other. But in a conformal field theory, all that continuous data of all the different types of measurements you can make that depend on continuous parameters actually gets reduced to depending on a discrete set of data. Now, it's actually an infinite discrete set, but this is still a huge simplification and very helpful. So our goal, then, is to try to figure out what these numbers are. So in general, it can be very hard to compute these numbers from first principles, and we have to measure them. There are some examples of conformal field theories where you can compute these numbers using traditional field theory techniques, namely Feynman diagrams. But actually, that's just a small class. Most of the time, you can't use Feynman diagrams. And for example, in the 3D Ising model, you can't use Feynman diagrams. They're not going to get you very far. So you need something else. The approach that we're going to explore is a very old one due to Polyakov in the 70s. It's called the Conformal Bootstrap. And the idea is to just put together as many consistency conditions, mathematical and physical consistency conditions, as you can on these numbers. Once you get enough of them, maybe you can solve those conditions for the numbers, or at least constrain the numbers using those consistency conditions. So it's basically putting constraints on the answer instead of trying to work from some starting point towards the answer. And one of the things about the bootstrap that I really like is that it only makes reference to these numbers. It doesn't make reference to the microscopic system you started with. And that makes sense with the idea of universality. The idea of universality is that it shouldn't matter whether you look at water or the Ising model or a magnet. Somehow the same numbers have to appear. So that means it's probably not a good idea to spend too much of your time trying to simulate water molecules bouncing off of each other at the critical point. Instead, you want a different starting point. And the idea here is to kind of try to constrain the answer. So because it just refers to these numbers and there's no specific constraint on the type of theory going in, it works without Feynman diagrams. So it's non-perturbative. It has a chance of applying to theories like the Ising model. And actually, the bootstrap approach had some huge success in the decades following Polyakov's work. In particular, in two-dimensional CFTs, where conformal symmetry is extremely powerful. It's powerful enough that the 2D Ising CFT was exactly solved. Now, the 2D Ising model, this is this is a situation where the 2D Ising model itself, not just the CFT, was previously solved by Onsager. But the bootstrap approach is much simpler and qualitatively different, and suffices if you just want to learn about the critical point. So the bootstrap, that's sort of the poster child for the bootstrap approach. You can solve the 2D Ising model. And there's a partial classification of 2D critical points using this approach. But there really wasn't much progress on higher dimensional critical points for a long time, until a few years ago, when a huge revival began.
What do you mean by partial classification?
So what I mean is, so actually it refers to this idea of the number of degrees of freedom that you asked about earlier. So there's a measure of the number of degrees of freedom in a 2D CFT called the central charge. And there's a complete classification of 2D CFTs with central charge less than 1. But there's a huge unknown zoo with dragons and monsters for a central charge greater than 1. We know very little about that. Okay, so let me talk about this new revival and the new techniques that we have. Any questions before I continue? Okay. So the idea of this revival sort of started with a lowering of standards. So instead of trying to solve the CFT completely, to just solve for the numbers exactly, instead we try to get some information about it. Maybe not all the information, just some. So this group, Bertazzi, Richkoff, Tony, and Vicky in 2008, showed that one could define an oracle. One could construct an oracle that can answer partial questions about CFTs. And the question that the oracle answers is, well, what you do is you take a list of numbers and you ask, is this list of numbers possibly part of the spectrum of a CFT? By spectrum, I just mean the list of dimensions. And remember, dimensions are related to critical exponents. So we're trying to compute these deltas. So we take a list of hypothetical deltas and we ask, is this list possible in a CFT? And the oracle says either no, absolutely not, you cannot have that list of deltas, or maybe, I don't know, maybe. Those are the two choices. And the idea is that if you have this oracle, it's actually extremely useful, because what you can do is you can choose different deltas and you can feed them into the oracle. And every time it says no, you cross out that part of delta space. And so you cross out many, many, many points and so on, and you build a map of the allowed region of deltas. And so this oracle uses something called the conformal block decomposition of a 4-point function. And so what I'm going to try to do over the next few slides is describe what that is and how it's useful for answering these questions. Yes?
Is that a partial list or a complete list? Do you have some knowledge about what primary fields or something like this in order to feed this oracle information?
Right. So that's a great question. So one of the important properties of the oracle is that you don't have to ask about the whole spectrum. So you can just ask, is it possible for the first operator to have dimension 2? Well, I don't know anything about any of the other operators. And the oracle will still give you the answer. So you only give finite lists to the oracle, even though the spectrum of a CFT is infinite. That's right.
The deltas are real numbers, right?
Yes.
So just knowing a bunch of points that they don't work, they cannot reduce the space.
Right. So then what you need is to do a little bit of work to show that there's some kind of, once you've ruled out a delta, there's an open ball around that delta that you can also rule out. And that you can in principle do.
So in sense of understanding that integrated, all critical space need not be conformal in higher than 2 dimensions. Is that right or not?
All critical theories may not be conformal.
Power loss of some correlation.
Right. So by critical, you mean scale invariant?
Yes.
If you like.
Higher than 2 dimensions.
That's right. So that's a great question. So whether scale implies conformal invariance is an open problem. For the purposes of this talk, I'm going to assume that it does, or at least I'm going to restrict to classes of theories for which it's true. It's been proven in 2 dimensions for theories satisfying certain conditions, and also proven in 4 dimensions, but it's still open question in 3 dimensions. Okay, so I said I would talk about the conformal block decomposition, because that's the sort of key element that's used in this oracle. And a good warm-up for understanding the conformal block decomposition is to think about the spectral decomposition of a 2-point function in quantum field theory. So apologies to those of you who haven't seen quantum field theory. This is in the first few chapters of Peskin, for those of you who have. The idea is we look at a 2-point correlation function, and we do the only thing we know how to do in quantum mechanics without more structure, which is just insert a complete set of states. And the states so now I'm in a quantum field theory, and it's not a conformal field theory. It's just some general quantum field theory. The states in a general quantum field theory are classified by their mass. For each mass, you can have some momentum. And the energy lies on the mass shelf. OK, so we have these states, and we classify them according to their mass and their spatial momentum, and insert them between these 2 operators. And the nice thing about classifying states according to their symmetry properties is then the overlap between states and operators is completely fixed by symmetries. So if you compute this overlap between the operator that we're interested in and the state with some mass and momentum, it's completely fixed up to some constant. And so we can take this thing that's fixed by symmetries and stick it in here and compute what we get. And this is the result. So the result has 2 pieces. One piece is called the Feynman propagator. And this is the piece that's completely fixed by symmetry. So it just comes from this exponential and doing the integral, and that's it. And it gives you this interesting function. There's another piece that is not fixed by symmetries, and that comes from the coefficients here. So we don't know the coefficients, but we put them together, and the square of the coefficients gives this thing rho of m. And we don't really know what rho of m is in a general theory, but we actually do have one piece of information about rho of m, which is written here off the slide. The statement is that rho of m is positive. And the reason it's positive is because it's a square of these coefficients. These coefficients, well, it's the absolute value square of these coefficients. So in a unitary theory, where this insertion makes sense, this thing has to be positive. Okay, so determined by symmetry, unknown but positive. That's the idea that I want to emphasize. And the next slide, which is about conformal field theories and 4-point functions, looks exactly the same. Just the equations have been replaced with a few things. So the idea is that we now have a 4-point correlation function, and we insert a complete set of states, and we classify those states using symmetries. Except now the symmetries are different. Instead of just Poincare symmetry, we have conformal symmetry. And so the quantum numbers are not just mass and momentum, but they actually turn out to be dimension and spin. So some discrete numbers here. So we insert this complete set of states, and the nice thing about classifying them according to symmetries is that symmetry then fixes the overlap between the operators we're measuring and the state. So this is now fixed up to a constant. So when we insert that thing into this sum and do the sum, we get something with the same structure as before. We have something that's known. It's a known function. It's just some special function called a conformal block. And that's the analog of the Feynman propagator. And then there's some unknowns that have to do with the coefficients in these overlaps. And we don't know what the unknowns are, but we do know that they're positive. So that's called the conformal block decomposition. It just follows from principles of quantum mechanics and symmetry. But there's something special about 4-point functions that we couldn't do with 2-point functions, which is that we can insert this complete set of states in different ways. So let's look at our 4-point correlation function. And the idea for inserting a complete set of states in quantum field theory is you basically split up the space into two pieces, and you think about what can live between the two pieces. So the states live on this line here. I've split up the space from left to right, and states live here on this line in between. And I can compute this 4-point function by doing this. And when I do that, I get a sum of these special functions, conformal blocks, with these unknown but positive coefficients. But I can also split up the space differently. I can split it up this way and insert the states on this line. And then I get another expression for the same 4-point function in terms of conformal blocks with positive coefficients. But it's a different expression because I split up the space in a different way. And in particular, the way these two expressions differ is in one case, I have a conformal block of all the 4 points. And in the other case, I have the same special function, but where x1 and x3 have been swapped with each other. So this gives a consistency condition on my theory. This consistency condition had better be satisfied in any consistent theory. And it's the reason why someone can't just come up to you and hand you a list of deltas and f's, this discrete data that defines the CFT. They can't just come up to you and hand you a list and say, there you go, there's a CFT. You have to check first whether this consistency condition is satisfied. And this is the condition that Polyakov wrote down when he first proposed this bootstrap approach. The idea is to study this condition, which is extremely constraining, and use it to carve out the space of possible scaling dimensions. And I just want to emphasize the structure of this equation is that the stuff in parentheses here is known. It's a bunch of special functions that you can look up in Wikipedia if you like. It multiplies some positive but unknown things. So what the oracle does is we don't have a lot that we're starting with, but the oracles can make progress with just this little amount of information. And the idea is to really look at this equation very abstractly and say, OK, we have some stuff that we know. They're functions. But we can think of them as vectors in the vector space of functions of 4 points. So we just draw each of these different f's as some vector. And then they have positive coefficients. And we're trying to solve this equation, this sort of like balance of forces equation with positive coefficients. And sometimes it's possible to solve this, and sometimes it's not. So on the left is an example where it is possible to solve this equation with positive coefficients. So we write out all the vectors corresponding to all these different deltas. And then we try to see if they can balance. And in this case, they can. And on the right is an example where they can't. And the way to see that they can't balance is to look for a separating plane. So we look for a plane alpha such that all the vectors lie on one side of the plane. So the way the oracle works is you give it a list of deltas. It constructs all the vectors in that list. And then it also constructs all the other vectors that could possibly appear. And then it asks the question, do they all lie on the same side of some plane? And if they all lie on the same side of a plane, then there's a problem. The list you gave it was inconsistent. So the problem of finding this, so the key is to find this separating plane. And this is basically a problem of solving a bunch of linear inequalities. We do that on a computer using linear or semi-definite programming. So in general, to get the most interesting constraints, this is some very, very high-dimensional set of inequalities, and we really need a computer to do it. A hope for the future is to come up with some better analytical understanding of these constraints and maybe do away with the computer. But for now, we definitely need a computer. Linear programming, by the way, is the type of optimization thing that airlines do to figure out how much to charge you for your plane tickets. OK. So that was very technical. I apologize. That was definitely the most technical part of the talk. Are there any questions before I continue? Yes?
So you mentioned the delta could be 2. What if you screw up and instead of giving the machine 2, you give 2.001?
Right.
And it says no.
That's right. So
it's kind of the opposite of the complementary
Right, so that's the situation you want. So you want a situation where you want to know the boundaries of the allowed space and the disallowed space. So if you put in 2 and it says maybe, and then you put in 2.0001 and it says no, you know that there's a bound.
Right, but what if the number, my question is, the deltas are discrete points on your infinite dimensional space?
So you want to know exactly where the crossover is.
Well, no, I want to know the deltas. I guess you want to know the deltas.
Yeah. So, okay, so let me get a little farther into talk and we'll see how we actually determine the deltas. So we're not, I should say, we can't determine them exactly. The best we can get are bounds.
So do we know some topology of like this that's connected? That you were talking about like boundaries and stuff. Do we know that there's...
Yeah, that's a really good question. So actually, I don't really know very much about the topology that we expect for these spaces. Mostly it's an experimental science at this point, making these plots that I'll show you in a few slides. That's a great question. Other questions?
Technically, we should be able to do the same thing for the Fs with like 6-point functions, right?
Right. Okay. So that's also an excellent question. So because of the way, if you can solve these consistency equations, so remember we had this equation, this thing that we're trying to solve on the bottom. If you can solve this for all possible 4-point functions, it actually implies consistency of all n-point functions. So this is, Polyakov also noticed this, that these are really the only consistency conditions you have to solve. And again, it's a vast simplification over general quantum field theories, because it means that to write down a conformal field theory, you just need to solve a discrete set of equations. Whereas in general, for quantum field theories, we have no idea what the general classification of quantum field theories is.
And this is true for every dimension?
For every space-time dimension. Yeah, that's right. Yeah, so this equation is true in every space-time dimension. The difference is that the special function that appears depends on the space-time dimension.
Does it work for different lattice? For example, 2D, there are hexagon lattice.
For different lattices?
Yeah, like hexagon, not square lattice.
Yes, so from this point of view, you don't see anything about the lattice. So the idea is that you're interested in studying just the universality classes, not the specific microscopic theories that live in those universality classes. So it might be that the Ising on the hexagonal lattice is the same as Ising on the cubic lattice at the critical point, but all you're trying to do is constrain the mathematical properties of the critical point, and that's it. So this is both an advantage and disadvantage. It means that I'm often having conversations where people come and like, what can you tell me about this specific theory with this Hamiltonian and these degrees of freedom? And the answer is probably nothing, other than these are the possible things you could get in that theory. OK, so that's how the oracle works. So here are some of its prophecies. So when we took this procedure and first applied it to CFTs in 3 dimensions, we got a big surprise. So let me just set the stage by reminding you that the assumptions that go into this plot are extremely general, and they don't include any information about any specific theory so far. So what we ask is just, what is the space of allowed scaling dimensions, delta sigma and delta epsilon, in a conformal field theory in 3 dimensions? And there's one other assumption that goes into this, which is that we're looking for theories with a Z2 symmetry. So in general, you can put in whatever symmetries you like, and you can study constraints on such theories. So we asked that question, and we studied the 4-point function of sigmas. And this is the result. So the claim is that the white region it's not possible to have a CFT in that region. So if you give the point 0.54, 1.8 to the oracle, it says definitely no. But if you give a point in this blue region to the oracle, it says, I have no idea. So you study many points and you make an exclusion plot. And this is the shape of the exclusion plot. And you can see that it has an interesting feature. And this interesting feature occurs at about 0.518, 1.41. And those points we know from Monte Carlo simulations and experiments are very close to the observed values in 3D Ising universality class. So this is a hint that somehow these very general techniques knew something about a special theory, the 3D Ising model. And it's exciting because the 3D Ising model is not accessible using, it's hard to access using other techniques. There are other methods that people have for trying to study the 3D Ising model, but they all have different types of shortcomings. And this is a qualitatively new way of learning about it.
Should I feel bothered or something angry?
Should you feel bothered? You should feel happy. So one thing that could have happened is the bound could have been up here, and then the 3D Ising model would have been somewhere in the interior, and we wouldn't really have learned anything. The surprising thing that still remains unexplained, even 5 years later, is that the 3D Ising model is so close to saturating the bound. We don't know why, but it's actually great that it is. Yes?
So this seeming cost represents an intersection of two bounds?
Yes. So in 2 dimensions, there is an analytical understanding of part of the analogous plot. So there's a similar plot in 2 dimensions. It looks the same. And in 2 dimensions, you can describe analytically what this line is. And yes, there is indeed a nice curve. It's a straight line in 2 dimensions that makes this part of the plot. In 2 dimensions, we don't know what makes this part of the plot. But it's possible you could come up with some description of it. And so yeah, in that case, it definitely is an intersection of 2 things. The understanding in 3 dimensions is much sketchier. Yes?
Do you at least have an example of something inside the maybe region?
OK, yeah, many, many examples inside the maybe region. So the easiest way to construct examples is to look at the line delta epsilon equals 2 delta sigma. So that's down here somewhere. On that line, there are an infinite number of theories with a large number of degrees of freedom, like the type I mentioned at the beginning of the talk. So if you're willing to use large numbers of degrees of freedom, you can fill out this area very easily. Away from special limits, like perturbative limits or large n limits, there isn't actually a lot known. You need to simulate your favorite lattice theory and try to make measurements, and that's actually quite hard. But there are some other theories that are known about, and I'll show plots of those later.
I guess I have a question related to what Phil was asking. Is there something special that the 3D Ising model ended up where they do intersect, or that's just
So again, we don't actually know why this happened. We don't really know why this happened. I mean, it seems that basically the statement is that the 3D Ising model appears to be the CFT that maximizes the difference in scaling dimensions in this direction.
Let me ask a slightly different question. If I expanded the range over which you did the simulation, are there any other interesting points like this?
Right. So on this plot, we've extended the plot for a while, and no, we don't see any other interesting points. But you can make different plots assuming different symmetries, and then yes, you can see other points. But yeah, I'll leave it there. Yes.
Sorry. Isn't that the idea behind linear programming? Is you check out the intersection points?
Yes, that's true. So the map between the space that we do linear programming on, which is the space that these high-dimensional vectors live in, and this space is a bit complicated. Roughly, this is some kind of low-dimensional slice of that very high-dimensional space.
Sure.
So it may be that the corners of the high-dimensional space don't actually correspond with the low-dimensional slice. The low-dimensional slice might cut through edges and faces and stuff like that.
But this could be a nice slice of that.
Possibly, yeah. Yes?
There are all sorts of inequalities for critical exponents that were derived by various people in sort of various assumptions. Do they help to locate that point?
Good. So yeah. So any information you have about any additional information you have about critical exponents, you can use. So you can put in that information and get better results out, and I'll show you that on the next few slides. One piece of information that I used implicitly here is an old bound on the critical exponents that says that every scalar operator has to have dimension greater than a half in 3 dimensions. So that's, that allowed me to ignore that part of the plot. That's one example. That example, that greater than a half bound is called the unitarity bound. That actually just follows from conformal symmetry. So it's very powerful. There are other types of constraints that come from studying some specific lattice model that might also be what you're referring to. And I actually don't know of any instances in which those have been used to help, but it's possible that they could. If you had powerful enough theorems, you could use them.
Do we know anything that conformal bootstrap is powerful enough to give us exactly what the space is?
So in 2 dimensions, yes. The conformal bootstrap approach is powerful enough to give exact answers for certain CFTs. But it's not using this approach, not using this oracle idea. There you have extra structure, and you can make more progress using that extra structure.
Well, 2-dimensional theories, not 2-dimensional depths.
That's right, 2-dimensional theories, yeah. OK, good. So that previous plot was just looking at a single 4-point function, this one, 4 sigmas. One thing you can ask is, in a CFT, there are actually an infinite number of consistency conditions associated with other 4-point functions, and what happens if you put those in. And this is what you get if you study this larger system of 4-point functions. And you additionally put in one interesting piece of physical information, which is that sigma and epsilon are the only operators with dimension less than 3 in the theory. And this actually, that sounds like a technical condition, but it comes from a very simple observation. So the number of operators with dimension less than the space-time dimension, which is 3 in this case, is equal to the number of dimensions of the phase diagram. So water has a 2-dimensional phase diagram because there's the temperature and the pressure. And so that means there are 2 operators with dimension less than 3 in water. So that's a very rough observation that we can make about the 3D Ising model. That's definitely true. We can put that information in, and it's helpful. So in particular, what it does is it actually gets rid, before we had this big, large allowed region, and now putting in this extra information and studying these extra correlation functions, you actually get, instead, an island. And then there's some other region over here. But we know from other ways of studying the Ising model that the Ising model definitely lives in the island. And that's extremely powerful because now the island is like a determination of the critical exponents. You can look at the island and see how large it is and where it is, and that gives you an estimate of these scaling dimensions. And over the last few years, we've just basically taken this same technique and this same computation and tried to push it a little farther. And this is the result. OK, Acrobat Reader doesn't want to show you the result. Let's see. So you get the idea. So the different colors are, those are a series of bounds that were computed one after another using more and more powerful techniques, more and more powerful algorithms.
There's no levels of confidence.
There are levels of confidence, that's right, where you're 100% confident in each level once you've figured out where it is. So this is the final result. Well, it's final as of now. The island keeps shrinking. And currently, this is the size of the island. And for reference, these are the error bars on the best Monte Carlo simulations. which have been refined over decades and decades and are really extremely impressive. And I should say the presence of these excellent Monte Carlo results has been incredibly useful. So I do not want to say anything bad about them. It's great that they're there. But this rectangle is a lot larger than the Bootstrap island, which is just down here. And looking at the size of the island gives you a determination of the critical exponents to very high precision. So, of course, eventually we would like to shrink this island to a point. Probably to do that, we need better analytical tools, not just numerical tools. But in the meantime, if we like, we can throw bigger and bigger computers at this problem and shrink the island more and more and get more digits.
Do we know that there is only one conformal field theory existed in that island? Maybe there is still more.
In the island?
Yeah.
That's an excellent question. Right. Maybe there's more than one conformal field theory in the island. As the island continues to shrink, I think it gives less and less confidence to that idea. The fact that there's a tiny island there is strong evidence that there's a unique conformal field theory in this regime. And that actually leads me back to the idea from the beginning of the talk of critical universality. This is in some sense an explanation of critical universality in a wide class of systems. And the idea is that suppose, well, it relies on some conjectures, but suppose we know that we have a theory that has a critical point, so it displays scale invariance. And suppose that we know or can prove that scale invariance implies conformal invariance. And suppose we make some very rough measurements of the system. So we know that it has a Z2 symmetry and it has operators with dimension around 1.1 to 1.5 and so on. Then it follows from these results that the critical exponents, the dimensions, actually live in this island, and presumably in an even smaller island. So it means that many different systems really all have to map to this one point if they obey these assumptions. So that basically the reason that the same numbers appear in boiling water and magnets is that these are the only numbers you could have.
Or
yes.
Maybe there is an infinite number of numbers in there.
Maybe there is.
Very close to each other.
That would be amazing. Actually, another possibility is that maybe the island disappears. So that would imply that the assumptions are wrong, that there is no conformal invariance in any of these systems, which would be also very interesting. But upon seeing this, John Carty encouraged me to stop in case that happened. Yes?
Two questions. One is, in the case of water, there is no exact Z2 symmetry.
Yeah.
And so you have to tune into some critical point in order to get it. And so how does it tell, what does it tell about the applicability?
Right. So that's a very good question. So from the point of view of the Bootstrap and CFTs, you can, to some extent, explain why that happens. The idea is that, so the Z2 symmetry is stable at the critical point if there are no Z2 odd operators that are relevant. So that's a question purely about the CFT data, about the dimensions. So if you were to go and classify CFTs and you found this CFT as part of your classification, you would look and you would go, let's see, how many Z2 odd operators does it have? Well, it has one sigma, which is dimension less than 3. And that's the only relevant Z2 odd operator that it has. And what that means is that to reach this theory, you can guarantee Z2 symmetry if you tune one parameter. And you know that just from the CFT. And then that's true. In water, you have to tune a one parameter direction in the temperature pressure plane to get the Z2 symmetry. Yes?
Yeah, so, and the second question is, what did you get, to get this decrease in bounds, what did you have to make? What
You mean as we shrink the island, what are the differences? So in that movie, there were no new assumptions, just more powerful, just faster algorithms and faster computers.
So did you take more points for dimensional space or what?
Good. So yeah, basically what you do is you have these constraint equations that you're trying to solve, and the equations are they're equations among vectors. And these vectors live in an infinite dimensional space because they're vectors in the space of functions. So to put them on a computer, we have to take a finite dimensional slice of this infinite dimensional space. And the larger slice you take, the stronger bounds you get. So basically, it has to do with how high dimensional the linear programming problem is.
Is there some built-in bias in how you sample, or is it just that the constraining power in some direction, like stretched this way? So you seem to have more errors in some direction. Is this a question of how you sample? It's more a question of it's more accurate in certain directions in parameter space than others.
So I don't know the answer to that question. It's the type of thing that you might. I think that. Yeah, I don't know the answer. It's the type of thing you might try to attack with some better analytical understanding of the crossing equations. Yes.
Because a related question was, it looked like the shape in your movie stayed the same, it just shrank.
Right. Yeah, I don't know why.
There's like some notion of distance or something. Seems like.
Yeah, these are all really good questions, and I don't know the answers.
Yeah, monoliths are supposed to be rectangular.
You had a question. Yes. So in 2D, you can also get an island, but the assumptions that you have to make seem to be a little bit different. So it's not actually sufficient to make the analogous assumptions in 2D to get an island. You have to work a little harder and put in a little more information about the theory. And this is not a subject that we understand systematically. So the question of, if you have a specific type of theory that you're interested in, we don't know the answer of how many assumptions and what type of assumptions you have to put in to isolate that theory. And so that's something that people are still exploring. OK, so I just talked about these two operators, sigma and epsilon. But you can go further and you can get more information about the CFT. So remember, the CFTs have an infinite list of operators. For condensed matter physics, you probably don't need to know very much about this infinite list, but it's definitely interesting for lots of other applications. This is an example of computation of dimensions of over 100 operators in a 3D Ising CFT. Some of these dimensions are known pretty well, and some of them are not known so well. The idea on this plot is that the larger circles represent bigger confidence. So we're pretty sure there's an operator there. So it's opposite from what you might usually expect. Basically, this works by doing a bunch of samples and superposing the samples. And if the samples lie on top of each other, you make the circle bigger. But this allows you to estimate many, many operators and get a picture of the spectrum of a non-perturbative theory, which is a new thing that we have. And there's a lot you can do with it. And it's really interesting to just stare at these pictures and try to understand some of the structure. Some of the structure actually has been understood using analytical techniques. So there's an interesting series of operators, which are these lowest operators here. So this is dimension minus spin. So these are basically the lowest dimension operators with each spin form a special class. And they can be studied analytically. And you can see a beautiful match between analytics, which leads to this curve, and the numerics. So this is something that's definitely just in its infancy and still very interesting and still ongoing, trying to pick apart analytically how the crossing equation works. And maybe if we unravel it enough, we can understand how to reproduce some of these numerical results purely without a computer. OK, so I talked about the 3D Ising model, but I've also mentioned other universality classes. There are many types of CFTs. They appear all over physics. They describe second-order phase transitions in condensed matter systems, which is what I focused on. CFTs are interesting in beyond the standard model model building. They're interesting for understanding what kind of dynamics could possibly occur beyond the standard model in some conjectural scenarios. There's also another way that CFTs are interesting that I put in the title of the talk because it sounds catchy, but I haven't spent any time on. CFTs encode theories of quantum gravity by the ADS-CFT correspondence. So these types of bootstrap questions of classifying CFTs can be translated into questions about classifying theories of quantum gravity, which is obviously interesting in its own right. And one of the other things that I like about CFTs is their landmarks in the space of physical theories. And there's a big program to basically try to understand the space of quantum field theories by starting with conformal field theories. And then once you understand a specific point very, very well, you can try to move away from it a little bit. The idea is that a general quantum field theory can be thought of as starting with a conformal field theory, deforming it, and flowing to long distances, and getting another conformal field theory. And so that gives you an idea for making a map of quantum field theories, of the space of quantum field theories. You start by studying these landmarks, and then you study the roads between them. And I mentioned other universality classes. These are some other examples of plots that we can make. These are other universality classes with different types of symmetries that also show up in their bootstrap bounds. These are theories with ON symmetry in 3 dimensions. The Ising model is the lowest member of this family here, so that Ising curve is down here at the bottom. And then there are analogous curves here. These error bars are the best results from Monte Carlo simulations and experiments. And I just want to mention one thing about this error bar. So this theory is called the O2 model, and it's actually the best experimentally studied critical system. It's the most precisely studied. And it describes the superfluid transition in liquid helium. And the reason it's the most precisely studied is because we have extremely precise measurements done on the space shuttle in 1993 for this theory. And they had to do them on the space shuttle because if you have a big vat of liquid helium, there's a pressure gradient on Earth. And the pressure gradient means that you can't tune the pressure of the whole system to criticality. Instead, you'll just have a tiny sliver of critical liquid. So instead, what you do is you go on the space shuttle, and then there's no pressure gradient, and then you can have the big block of system that you can study all at once. And so that's one example of really good science done on the space shuttle if you were looking for one.
What is that, Karen?
Oh yeah, good. So this is an example of a class of theories for which we also have some analytical techniques that work nicely. So there's a large N expansion in this theory, and that's what these dots are. And the large N expansion breaks down at small n. So the curve is the extrapolation of large N of the large N expansion to small n at some fixed order, and it disagrees badly with the correct answers. But it works beautifully up here, and so you can see another nice convergence between bootstrap results and analytic results. And then finally, a universality class that's really out there. This is a 6-dimensional maximally supersymmetric theory that is part of M theory. Very little is known about this. It's very hard to construct in the laboratory. I encourage you to try it. But this theory satisfies the axioms of conformal field theory, and so it's the type of thing you might try to study with the bootstrap. And this is an example of bootstrap bounds on this very exotic theory. So basically, over this last decade, the conformal bootstrap has turned into one of the few non-perturbative tools that we have in quantum field theory that works to give us rigorous results about strongly coupled theories. It relies on a different set of assumptions than other tools. So other tools include integrability, which requires a very, very special structure in your theory. supersymmetrical localization, which requires supersymmetry. They all have their overlapping regimes of applicability, and the Bootstrap gives a new regime that you can study. And in particular, these conformal theories you can study with the Bootstrap have intersect physics in many, many interesting ways: condensed matter physics, particle physics, and string theory. So thank you very much.
So before we have time for maybe one more question, for all